The question I have is, could you give some examples where the state of stress can be approximated into two-dimensional? Let's start with two approximations that are commonly used in the Cartesian framework, and they are called the plane stress approximation and the plane strain approximation. So what exactly are they? Supposing, say, I take this three-dimensional state of stress and look at what's going on this plane right here, right? X plane. If this is true on this X plane, then we say we have a plane stress condition. And on the other hand, if this is true on this plane, the X plane again, we say we have a plane strain condition. So what exactly is this? Well, number one, the two shear stress components must be zero. Number two, the normal stress sigma x must be a constant. So what exactly do we mean by constant, right? Well, due to any loading that takes place on this YZ plane, these stress components could keep changing, right? But this should not change. So what about the plane strain condition, right? Well, the shear stresses must still be zero, but in this case, the strain in the x direction is a constant. So if the strain is constant, we call this a plane strain condition. Since in each of these cases, the changes that take place only in the YZ plane, it is sufficient to analyze the state of stress in the YZ plane. In other words, we have taken the 3D states of stresses and approximated them into this 2D state of stress. Here's an example of a plane strain problem. We have a concrete dam that is very long in this direction, but it has the same cross-section throughout in the x direction. Typically, the dam will be kind of fixed over here through some kind of abutment, and similarly on the other side. So when you have something like this, the plane strain condition is a pretty good approximation for this. The shear stresses on the YZ plane can be neglected, and the strain in the x direction can be assumed to be a constant. So all we have to do is to take a little differential element in the YZ plane and analyze the state of stress on that plane. Of course, near the abutments at the ends of the concrete dam, things will be three-dimensional, and you won't be able to capture the three-dimensional variations of stresses using a two-dimensional analysis like this. Usually you have to resort to an advanced analysis technique like the finite element to capture the three-dimensional nature of the variations of the stresses between the abutments and the concrete dam. Here is another example where the analysis simplifies a lot if we use a cylindrical coordinate system. We have a cylindrical shaft subjected to a torque at the end. The only stress component, non-zero stress component produced by this torque is indicated on this differential element drawn with respect to the cylindrical coordinate system r theta z. You might recall from your torsional analysis that the shear stress produced by the torque T goes around in circles on this plane, right? And this is the only non-zero stress. So this stress right here, for example, is the stress that acts on the z plane in the theta direction, right? And this is the complementary shear stress. So all we need to do here is to take the differential element in the z theta plane and analyze it. And that's what this is. If I just call the z-axis as the x-axis and the theta axis as the y-axis, the only non-zero stress component that acts on this differential element is tau xy, which is tau z theta that you see over here. So you can see the stress analysis for this torsional problem boils down to this simple two-dimensional stress analysis. So here's my third example, pressurized thin-walled cylindrical vessel. The cylindrical coordinate system will be the most efficient system to analyze this problem. Now denoting the axial coordinate as z, radial coordinate as r, and the hoop coordinate as theta. If I were to mark the stresses in a differential element drawn with respect to this cylindrical coordinate system, you might recall from your analysis that this is what we have. We have a normal stress in the z direction and a normal stress in the theta direction. So this theta stress is usually called the hoop stress, and this stress in the z direction is usually called the longitudinal stress. We might also recall that these stresses are given by these simple formulas. And here P is the internal pressure, R is the radius of the cylinder, T is the wall thickness. So there are only two non-zero stress components for the state of stress at a point like that. Once again, you can see all we need to do is to analyze the state of stresses in the two-dimensional z theta plane. That's what I'm showing over here. This is the z-axis, this is the theta axis. Now if I were to call the z-axis as x-axis and theta axis as y-axis, then it kind of boils down to the standard two-dimensional stress analysis problem. You have sigma x over here, sigma y over there. My final example here concerns bending of beams. Let's consider two different cases here. In the first case, we have a element of beam subjected to what we call pure bending. And in the second case, we have a typical beam problem where on a cross-section like the one that is taken at point A, you're going to have both the shear force B and the bending moment M. Defining a coordinate system, x, y, z system like shown in this picture, and considering a little differential element on that cross-section with respect to this coordinate system, only non-zero stress component would be this stress right here, sigma xx. This is the bending stress. Later you will learn that a simple formula like this, called the bending formula, would allow you to calculate a value for sigma xx. There are no other stress components acting on this differential element. But in a typical beam problem, in addition to the stress sigma xx produced by the bending moment M, there will be a shear stress tau xy that will be produced by the shear force B. Using the principle of superposition that you will learn later, that these two can be calculated separately using simple formulas like this and superposed. There are no stresses acting on this plane, the z-plane, plane perpendicular to the z-axis. So now you can see very easily that the stress at a certain point within the beam can be analyzed using the two-dimensional state of stress like shown in this picture. In other words, we just have to consider a differential element in the xy plane. That will be this element right there, right? So we have normal stress produced by the bending moment, and if you do have the shear force, then there's going to be a shear stress tau xy due to that shear force. Now you can see these are some of the common problems we run into in basic strength of materials like this course, and in most cases the problems will boil down to two-dimensional problems. But to define the two-dimensional problem correctly, what is required is a clear understanding of the underlying mechanics.